Hi, my name is Norman Corin, and I'm the founder and chief technology officer of Imatest. I'm going to describe the new Simatest program, which is a part of Imatest Master. And Simatest simulates complete camera systems, including lens degradation, image sensor noise, and image signal processing, which we'll call ISP for this presentation. This enables soft prototyping of imaging systems before they're built, and it allows rather thorough exploration of the effects of image signal processing blocks and operations. Simatest can display visual results, for example, the input and output images side by side enlarged, or it can send results for modules for calculating numerical performance, such as MTF, modulation transfer function, information metrics, photon transfer curve, etc. We will show a block diagram of Simatest. Then we'll discuss the physical properties. These are the properties of the lens and image sensor that you can't change as freely as image signal processing. We'll look at some of the outputs, and then we'll give a demonstration of Simatest. Here is the block diagram. On the left, you see the inputs to Simatest, or the input images to Simatest. And there are three types of images, actually four, that we describe here. There are raw or minimally processed camera images. These images are acquired from cameras and have noise and whatever degradation the lens has. These images are actually used to calculate the physical properties of the camera. There's also a pure simulated image that is essentially a perfect image. For that, you have to add simulated blur and simulated image sensor noise. Or there's a simulated image run through a lens design program, such as Code 5. For that, you still have to add the simulated image sensor noise. And when you have these images read in and the physical properties accounted for, then you can apply a variety of image processing blocks through Simatest. I will describe these in a bit more detail when I do the demonstration and show the Simatest settings windows. The outputs that are available are a visual assessment, like the output and input images side by side, miscellaneous analyses relating output and input performed within Simatest, and two major external modules, color tone, which lets you look at things like the photon transfer curve, quite critical for calculating image sensor noise, and res charts, where we can measure MTF, noise, image information metrics, and a good many other results. Now, the physical properties in Simatest are very important, and these are the properties of the lens and the image sensor that are not so easy to change, although you can change them for what-if cases, but it's not quite like ISP blocks where you can change them quite freely and try whatever you want. So the physical properties must be added to all simulated images. They're included in acquired images, and so they're a part of them, and they don't need to be added when you acquire an image. The key physical property is the image sensor noise, and we have derived a sophisticated model of image sensor noise, which is compatible with the EMVA 1288 standard. This model combines dark noise, photon shot noise, and PRNU fixed pattern noise, and provides a really accurate performance model of the image sensor. Now, it's calculated from one or sometimes more undemosaic raw images of a grayscale test chart, typically a 36-patch dynamic range test chart. And an optimizer is used to find the coefficients for the three individual noise sources that we just mentioned. It really is very powerful, and will show the advantages of using it. We can also look at the color balance, which is a property of the image sensor and the illumination. That is derived from the same raw image as the image sensor noise coefficients. We can look at blur, which either comes from a lens design program, or we can approximate it by matching a demosaicked and minimally processed raw image. That's what we have done in the example here. We can also make an adjustment in exposure to match the input image. This is a less critical adjustment. The key thing is you need to know the physical properties of the system when you are running the Simatest simulator. Here's a quick summary of the outputs that we'll be showing you. As we've mentioned, you can do visual assessment. We can do several analyses within Simatest. The box here on the right shows some of the analyses we can do, which include comparisons, visual comparisons, MTF, structural similarity, and a number of other interesting things. More importantly, I think we can directly send the image very quickly to Imatest module, including image statistics, res charts, and color tone. And we'll be illustrating those in the demonstration. Now here's a quick outline of the demonstration. We'll start with a tour of Simatest, showing the main settings window and how to change the settings. Also how to open color tone to display image sensor noise, which is quite critical to the system performance. Then we'll show how we calculate the image sensor noise parameters using a raw grayscale test chart image with color tone. We'll compare res charts results, edge, MTF, and particularly information metrics for acquired and Simatest simulated images at low and high ISO speeds. ISO 100 is the low speed, 3200 is a very high speed that makes images quite noisy. It's equivalent to running in dim light. And finally, we'll do a quick demonstration of the effects of sharpening. The link shown here and in the QR code has more information. It's the Simatest overview. That's pretty easy to find in the Imatest documentation page. Now we're going to open Imatest so that we can run Simatest. So this is the Imatest opening window. We've selected a number of images that we intend to analyze. And the first thing we're going to do is open Simatest in the Utilities dropdown. Okay, this is the Simatest opening window. It has a brief description of some of Simatest's capabilities, and it also shows saved settings that are a set of sequences of ISP blocks that we're going to apply to the image. The first thing we typically do is read the image file. And the file that we're going to read is a image that's very similar to the 36-patch dynamic range test chart. It has a little bit different size and dynamic range, but essentially produces the same results. It also has slanted edges for measuring MTF and information capacity. And it has colors similar to color checker colors that we're not going to use for this demonstration. At this point, we open the Simatest settings window. And this is a fairly complex window with lots of different settings that we're going to run through very briefly. So the settings fill most of the window, but the window on the upper right, the image signal processing or ISP blocks window, that shows the operations that are going to be performed. Operations that begin with a % sign have been disabled. You can say, select an operation, enable it, or disable it. And so those are kept there for convenience. There's actually more lines in this ISP blocks window than are needed, and we have them there because we can move entries down or up, we can delete them, we can clear them, we can insert a blank line to make more space. As we've mentioned, we can enable and disable them. So it's very versatile, although perhaps not quite as slick as a window that would allow you to move blocks around. It was fairly fast to implement. So here are the available settings, and I apologize, there are quite a lot of them. You need to enter the input gamma. 0.45 is the inverse of the 2.2 display gamma, and that's what we use in the image that we use for the input, shown here in the main window. You can adjust the exposure. In this case, you can do a slight adjustment for the actual, comparing with an actual image, or you can do large adjustments to examine the effects of very dim light performance, where you boost the analog gain. You can do mosaicing, which is creating a synthesized Bayer raw file, or demosaicing using the standard MATLAB demosaicing routine. You can set the RGB balance, and that's measured from the raw image, and that's very important to set before adding the noise. You can adjust the gamma. We'll show how that's important. You can add fog, which simulates veiling glare. You can convert the image to monochrome. You can do automatic white balance. You can invert the image. You can set a breakpoint, which isn't that useful. We'll explain why. You can linearize the image. That's equivalent to setting gamma equals 1. You can resize the image, and you can add or correct a cosine fourth lens shading. And those are just the beginning. You can add noise, either simple noise, or in this case, I'm showing the image sensor noise that was measured from a raw image. We'll get to that a little bit later. You can also filter the image, apply a little bit of blur, and that also, the value was obtained by comparing it with a real image, demosaicked and minimally processed. You can add a color correction matrix. You can do 3 types of tone mapping. You can do one of 2 types of sharpening, or you can add one of 3 types of bilateral filters. It's very powerful, and we will be adding other functions as needed. Essentially, we have all of the functions that affect performance. There are some other functions that we will add that don't directly affect performance, such as geometric distortion, but we don't need those right now. Okay, I'll show you how we can set this window. For example, supposing we want to sharpen this image. I'm not going to use sharpening right now, but what we might do is adjust the sharpening radius. This is for standard sharpening, and adjust the amount of the sharpening. When we do an adjustment, the set window, which is used to set the ISP blocks in the upper right, turns red. And so it has to be set in order to complete this operation. So we will say put the sharpening block in line, let's just say 17. Okay, there it is. And if I kept it there, the image would be sharpened. For now, I don't want to use it. I can either disable it or simply clear it. We'll get to that later. If the auto update button on the lower right is checked, when you press OK, and if you've either set or cleared all of the settings that you've changed, it will let you go back to the main window, and it will perform the operations that we have listed, which I'll get to in just a minute. Okay, this is done. And what we've done is we've started with a regular RGB image with gamma equals 1 over 2.2 or 0.45. We've changed the gamma equal to 1. We've linearized it. We've put a bit of blur on it. This actually isn't important for measuring the image sensor noise parameters. We've done a slight adjustment of exposure. This is equivalent to the image that we're going to be acquiring. And then we've done an RGB multiplier. This again has been derived from a real image. We then do Bayer RGB, and this is the mosaicing or remosaicing step that creates the synthetic image. And finally, we add the noise, and we'll show you shortly how we actually determine the noise. Okay, so this is a raw image, and these big blocks you see are actually aliasing artifacts. If you zoom in, you see the characteristic shape of raw images. I'll double click to zoom back out. Now, this image can be saved using the save processed image, or in this case, we're going to open it in the color tone module. So I click on color tone, and color tone can analyze quite a large number of color and grayscale charts. We're going to stick with the 36 patch dynamic range setting, and we're going to analyze the image. We're going to keep it as a Bayer raw image. And then we see the detected regions. We're going to use these detected regions. We don't have to adjust them. It's automatically detected. So we'll do yes, express mode. So what you see here is a photon transfer curve. It takes advantage of a rather remarkable and great property of image sensors, which is that the noise in a flat patch is a function of the amplitude of the input signal, the average input signal, independently of the color. So all the colors are the same. This is called a photon transfer curve. And from this, using an optimizer, we calculate coefficients for the dark noise. This is this flat line. The photon shot noise, which increases with the square root of the signal, and the PRNU fixed pattern noise, which increases linearly with a signal. And so we get a very good fit. In fact, the fit is good enough, you can hardly even see the fit curve here. Okay, I'm going to save this image because I need to reopen this to run a real image that we're going to compare it with. So I'll click on Save Screen. I'm going to save the screen image and move it aside for comparison for later. Okay, now I'm going to close this. I think for the moment I'm going to close the Simatest window, and I am going to select the ISO 100. I think I need to click Select Images. No, that's okay, but I am going to choose the image to analyze. And so select analysis. I'm going to select a simple slanted edge analysis. And I've selected the image. I'm going to go ahead and analyze the image. And this will be analyzed in res charts, in the interactive SFR module of res charts. Now, it has read the raw image, which is a monochrome image. It asks, you want to use a standard monochrome image or work with it as a Bayer raw image. We're going to select Bayer raw. then it, okay, sorry, then it creates a monochrome image with raw data in it, which we're going to keep as Bayer raw. So we're going to say Bayer raw undemosaic RGGB. And here it is. This is with a, it looks dark because the gamma is 1. It's a linear image. And I am going to, I have to go back and change something. So I'm going to go back. Okay, I'm going to start in about 3 seconds. So our next step is to run color tone on an ISO 100 image. We're going to select the ISO 100 image, the raw image, to analyze. Okay, and now we have to select an analysis. In this case, we go down and we're going to select the 36 patch dynamic range analysis. We click on Analyze, and we are going to open it as a Bayer raw image. We now need to keep it as a Bayer raw image where we select a red in the R1, G1 channel. Here are the detected regions. And here is the photon transfer curve from the original image. Now, this is the image that we used to calculate the values that we entered into Simatest earlier. When we ran Simatest and then analyzed the synthesized image, we got a nearly identical curve. The dark noise is a little bit different. It's a bit higher in our synthesized image, but the other two noise types are very, very close. So what you see here is that using the noise model, you can very, very closely approximate the actual noise we get in the real image sensor. And this enables us to do a variety of things, including test out the image at very dim light or high ISO speeds, which are equivalent to dim light. Okay, so we're going to close this. I'm going to reopen Simatest and reread the same image file that we used before. And what I'm going to do now is in the settings, I'm going to, just to make it easy, I'm going to read some saved settings that I use to simulate a demosaic minimally processed image. Actually not very different from what we had before. When I do OK, and it calculates it, you can see that what we've done here is we've linearized the image, we've added the filter, adjusted the exposure. These are things we've done before, multiplied the RGB by the coloration of the raw image, added the noise, and then the two new things are we correct the color, we divide by the same coefficients that we multiplied by, and we change the image back to gamma equals 0.45. And what we don't do is remosaic and demosaic the image. So this is just a straight image. Now we can use this image to calculate res charts performance because we do have a good image sensor model. So we're going to open up res charts with this image. And we're actually going to perform two analyses that I'll show you. we will keep it at SFR and we will analyze the image. It has a saved region of interest for the slanted edge. So we're going to go through and analyze this slanted edge. And what you see here is an edge and the MTF. And important parameters are the information capacity for the 4:1 contrast, and also the information capacity Cmax, which is the maximum extrapolated information capacity. We're going to save this and compare this with the actual acquired image. So I'm going to save the screen and move it aside. One other item of interest that I'll show you but not keep is the spatially dependent noise. This is a rather important property that we can calculate that's used for the information metrics, information capacity, and related measurements. We'll go back to that. Now, I'm going to close this. Now for the next part, I'm going to look at the system performance of a slanted edge. And to do that, I'm going to reopen the Simatest window. And I'm going to read the same image file that we read before. I'm going to go into the settings. And what I had done is I had read some settings for the minimally processed demosaic image that are just a little bit different from the settings for the raw image that we analyzed for the image sensor noise model. Auto update is checked, so I'm going to click OK, and it's going to go through and do these settings. Okay, so what we can do is we can save this image if we want using saved processed image, or we can open it in the res charts window. And I'm going to be opening this as a demosaic image. So we have several types of analyses available. We're going to use the SFR analysis. Then we do yes to the analysis. We have settings, which we're not going to change. And then here is the edge and MTF for the ISO 100, the low ISO speed setting. We can also look at the edge and information capacity noise. And this noise is very important for the information metrics. It's described in the documentation on information capacity. But we're going to go back to the edge and MTF, and we're going to save it. So we'll do save screen, save, and I'm going to move it off the screen to compare. What I'm going to do next is synthetically, and I'm going to close, oops, I'm going to try closing, here it is, the res charts window. And I'm going to make some changes in the settings here so that we synthesize a very high ISO speed, 3200 window. And what I do to do that is I set the gain at a very low number. Actually, I'm going to use the exposure index. I set it at 0.03125, which is the inverse of 32, which is the multiplier for the high ISO speed. I'm going to put that setting in position 6, which is before the noise is added. So I'm going to do set 6, and you see I put it in position 6. Then I'm going to do the inverse of this, I'll put it in 17, which is simply after the RGB division. So this has inverse exposure of 0.0312. So it's actually a multiplier by 32. Now when I do OK, it goes through the whole process. It's essentially the same as we used for ISO 100, except we darkened the image here and we lightened it over here near the end. Now, this image should be quite noisy. And if you do a side-by-side view and enlarge it, the noise should be quite visible. And hopefully you can see the noise quite clearly on the screen. So now we're going to run ResCharts SFR again, essentially doing what we had done before. It's an RGB image, so we just say analyze the image. There's no other settings other than the region of interest. We'll do yes express mode, and we'll get similar results to what we had before, except that it's obviously noisy. So on the right is the ISO 100, on the left is the 3200 image. And the noise level, if we look at the edge and noise, is actually much higher than it was. Look, actually, the function looks the same, but the amplitude is much higher. So we will also save this one. We'll save the screen. And we'll do display screen in image viewer and move it aside. We're going to compare these two images with an actual acquired image that we use. We can close Simatest because now we're going to work with acquired images. So what we're going to be doing is selecting the slanted edge, and we have to select one of the images. We'll start out with the ISO 100 image. So we're going to read it in. Let's see. I need to do an analysis. Sometimes I have to, okay, I believe I have to reselect the image to do the analysis. Oh, okay, it's ready to analyze with a slanted edge. So I am going to read this image in, and this is a raw image, actually the same one we used for calculating the image sensor noise, but I'm going to read it as a color 24-bit image instead of a pure raw image. So it'll be a minimally processed RGB image. Here is the region which we've saved. You can see it by zooming in. So this is the low noise image, and we do yes express mode. And so what we see is the edge and the MTF that we can now compare with what we acquired or what we simulated. And what you see is that the rise distance is the same. That's because we actually use this image to calculate a blur. The MTF curve is somewhat differently shaped, but the MTF 50 is very, very close, around 0.32 or 0.33. Also, the information capacities are extremely close, 3.25 for the acquired image, 3.19 for the 4:1 contrast information capacity. For the simulated image, they're also quite close for the maximum information capacity. So we see very good agreement. Now, the interesting thing is what happens when we read the high ISO speed image. So we're just going to directly read that image file. We will also read the ISO 3200 raw image over here. we will convert it into a RGB image. It's essentially the same region of interest. You can zoom in on it, and we'll do yes express mode. And here we see the results for the real ISO 3200 image. Now, we'll compare those with the simulated results. So this is the image that you'd seen earlier where we showed you a side-by-side view. And this is the very noisy image. What I'm going to do then is open it in Res Charts, analyze it, and here you have the noisy simulated image at ISO 3200. Here is the real acquired image that we just did. And what you can see is that the MTF 50s are very close for these two images. There's a little bit of deviation, I think, because of the noise. The rise distance, again, they're close. There's some changes because of the noise. And the information capacities are also rather close. For the simulated image, the C4 is 1.04. It's 0.89 for the, actually, I have to look. This is the simulated image, and this one on the right is the acquired image. They're pretty similar, and it's actually hard to tell which is which. But what we have shown here is that we can simulate high ISO speeds or dim light with the Simatest noise model, and we get very satisfactory results. This can be extended so that low light measurements can now be done with Simatest, and we can actually predict the performance of cameras in low light. So with that, I'm going to wrap up the presentation. And essentially, the summary is Simatest is a powerful new tool with capabilities we are only starting to explore. You can use it to soft prototype camera systems before they are built. This should speed up and reduce the cost of designing cameras. You can explore ISP settings. This is partly an educational function, but every setting has its effects. For example, sharpening will make an image look sharper, but it'll worsen the noise. And an important part of it is we have developed a very powerful image sensor noise model, which is in fact compatible with EMVA 1288. That's an image sensor noise standard. And the noise parameters can be derived from EMVA measurements, but the measurements we do are much faster and somewhat less detailed than the EMVA measurements. And the noise model allows a rapid assessment of dim light performance. So we have a powerful new tool we're just learning how to use. Once again, the web page is in the Simatest overview. That's the best introduction. It has links to other pages, and you can reach it from the QR code. Thank you.